It's one in line. It's Joshua Mora. Joshua Mora is the CEO of System Stack, and he's going to talk about the taxonomy of errors for large-scale HPC AI environments. Joshua, so the stage is yours. You have an extra time. So we are between you and coffee, okay? Thank you.
Al mando. The person that was presenting, do you have the thing to change slides? Oh, it's right there? Okay. Thank you. All right. Awesome. All right, so I've got 21 slides, and I'll try to go fast and leave a lot of time for questions and a little bit of debate as well. The slides I'm going to present are supposed to be a little bit provocative, to have you thinking, and I hope you enjoy it. All right. So what are we going to talk in here is about all kinds of problems that happen at very large scale. Those problems also happen at small scale. However, they are not that noticeable, you know. So you may have observed some of the problems that I am mentioning, but those problems are way more visible and get in your way of getting the return of investment of your infrastructures as you scale. So what I want to show you in here is to make you aware of those problems, and as you keep working in this field, you will get to work on larger and larger clusters. So then the issues that we're going to be talking here, then maybe today you're not seeing them, but in a year from now or in 2 years from now, you may have the opportunity to work on a larger cluster, and then you're going to start seeing those issues. So this is basically giving you a presentation on type of errors, classifying those errors, and we're not going to talk about how we solve those errors. We're just going to talk about being aware of the existence of those errors, okay? And I'll give you also a methodology for quantifying the likelihood of running into some type of errors. So hopefully you will enjoy it. Okay, so I'm classifying, I don't know if you can see from far away the font size. I apologize for that. But I'm classifying errors by source, like where the errors are coming from, by type, like what kind of error it is, and then by how often the error is happening. This is just one way of classifying things. You could classify it in many other ways, but this is just one way of doing it. And then this sign plus, like 1 plus, 2 plus, 3 plus, this means how it impacts, how bad is that issue on your cluster. Imagine that you're trying to make money out of that cluster. So when you run into that particular type of error, you know, how often it happens, how hard it is that problem, and therefore what is the negative impact that it's going to have. So as you can see, for example, in here, this is one sign only, 1 plus, so these are hardware problems. Then system software failures, it gives you additional headaches. Software stacks that are designed and developed by the users, it gives you even more headaches. And then users not using properly the infrastructure, that also gives you a lot of headaches. So this is by where the error is coming from. This is by the type of error. You could configure something, whether it's the hardware or the software, not right. So that's one kind of headache. Another kind of headache is when a problem happens. It was unavoidable. Some component of hardware failed, a bug on the software happened. So these are unplanned downtime events. And then the last one, I call it degradation, which basically means things seem okay, they are working, but maybe not performing as they should. And then you're having that thing running for weeks, underperforming, okay? So that will hurt your business, okay? And your business can be just finishing your PhD in the right amount of time, by being able to complete your jobs, to get your papers published, and so on. And then the final classification is by frequency, how often that issue happens. So some things you've seen it only once in your life, or you see it only once or per year, or this is something I see on a monthly basis, or this is something I deal with it every week or even every day, all right? So obviously the more frequent, that's more obvious, it's gonna hurt you the most, all right? Okay, so we're gonna go really fast through some of this. On the hardware side, what I have done here is slice the machine in what I call tiers. And a tier is kind of a group of components within a group, within some section, physical section, that has a particular functionality. Like, for example, these are, I call it the CPU network tier. So basically, this is networking interfaces attached to the CPU side, for example, right? Then there's a CPU tier, basically CPUs, and then you got level 0 cache, level 1, level 2, level 3, and then you could think of something outside of or last level cache is like the DRAM. And then you got the coherency links as well, so I call that CPU tier. So basically, when I look for problems, then they are happening in specific tiers. It could be the accelerator tier. An accelerator could be a GPU or an ASIC or an FPGA, whatever you want. And then nowadays, you get these things. Before you did not used to have that, but that's kind of a custom type of interconnect for these accelerators. So it could be NVLinks, or it could be other kind of connectivity. And then this is just to provide connectivity inside, and then you got connectivity outside as well, okay? And then finally, you got a storage tier that connects on the CPU side and on the accelerator side. So that's kind of a way of describing general purpose this thing. And then you can have problems happening at any of these tiers, and within the tier at a particular component. And then when the problem happens, what kind of recovery you can have? Is it like requiring like a hard or a cold reset? Or can it be a soft, warm reset? So kind of something more lightweight. Again, I'm not going to get into how you solve the problem, but this is a different type of strategies. And then the other thing is, when the problem happens, what is the extent of the problem? Is it something that happens just localized, partially? Or this produced an event that changed into another one, and it affected another thing, and then affected another, so then it's more total, okay? So it's important to understand when a problem happens, the extent of the problem. So then you can later think about solutions. All right, moving into the software side, I separated between system software and user software. So just to make you aware, going from the hardware up, the first thing you got is BIOS and firmware. You may have a hypervisor or not. And then you have the drivers that are super tied up with the firmware to control the devices. Then you got system libraries, then you got operating system, and then the middleware. So what I'm trying to put in here is there's plenty of components from a software standpoint where software bugs exist. Therefore, problems are going to happen at any of these layers, all right? Again, it can happen also, you can look into when the bug happens, what kind of fix you could try to apply, okay? Is it a hard, cold, or soft one? Like, for example, what I mean with this hard reset is, imagine a driver on a device, and the device gets blocked. And then that device, when it got blocked, then it blocked another one. So then the whole system is locked, okay? So now if you want to recover from that, you may have to reset the machine, right? But sometimes it could be just a driver on a device that is loosely connected with other things, and it's just that particular device that got locked. You can reset the driver maybe on that particular device, and you can continue working. So there's different levels of resets that you can do. And again, what is the impact? Is it just affecting you on that particular library, for example, or is it something? I mean, the problem, the lower it happens, the higher the impact it's going to have. Okay, so the higher you are, then the less the impact you're going to have. All right, and then similar thing on the user side. You have, say, containers, user mode drivers, user libraries, applications, and then the workflows between applications. Problems can happen at any of these layers. all right? Again, what is the impact that it can have, whether it's localized, or you're creating a problem, a larger scale, that it can affect not only one machine, but also can trigger issues on other machines, especially because of the software. It's going to be asking for something to another machine, and it's going to create another problem in another machine as well. So sometimes it's like a detective type of work. All right, this is the fun one. User errors. So this is just certainly a long list of errors, and I think the system administrators may agree on some of those, maybe think that not, but let's go one by one. I think it's important. So there is why errors happen on the user side. So first, one of them, this is not in any particular order, it's just listing them. So there is a poor understanding of the hardware tiers and components. I mean, you're a scientist doing something, astrophysics, biochemistry, whatever it is, oil and gas. You care about your business. You don't care about what's the system. You want that thing to be like a black box. Submit your job, and hopefully it should run. That's ideal. But in practice, you want the users to have an understanding of those tiers and components, so then you can do a better usage or avoid having problems that is affecting you. Same thing with the software, poor understanding of the software stacks. You know, you may run this container that somebody else provided, but you don't know what was in that container, or it's bare metal and you don't know what's the software, or there's this thing that's connected with this other one and so on that the administrators put in place, and you're supposed to understand that, to leverage it, but you're not using it properly, and that creates problems. Poor documentation of processes. So you need to do something, it's a little bit sophisticated. You need to do first this step, and then another one. Well, don't change the order because things are going to fail, you know. Or this step, you go to this one, but you missed to put this step in the middle. So those create issues too. When something is complicated, and you do it manually, and then you need to do it again, and then again, likely you're going to run into doing typos, mistakes. So it's better to automate that. So teaching the users, once you got something properly working, make a script, and always use the script, and it will help you. A lot of people, they think, I'm going to do this only one time, so I'm not going to do a script for this. Well, you end up doing that multiple times, therefore you're going to run into issues multiple times, all right? Not many people uses profiling and monitoring tools, and those are important because it's an opportunity for you to learn how that thing is working. So then you can avoid issues and get that aha moment, oh, I didn't realize I was using this resource when running my application. So because they're not using these tools, no documentation about how to use those tools, then have a poor understanding of how the hardware and software works. So that creates problems, right? Poor understanding that some of those resources that they're using are shared. That basically means that the machine is not yours. The machine that you're using, there is a shared resource that is also being used by somebody else, like a network or storage. Therefore, you think that that thing is kind of protected for you to do your runs, but somebody else, not having also good understanding, it's creating a problem on your end. So that's another important issue. So I call it like a congestion problem in here. Another reason of poor understanding is we always have a finite or a limited amount of resources. And you may think that you have infinite amount of resources, and then your application is going to try to use infinite, or you could have a bug on the application that tries to use more and more memory, or more disk, or more cores, but there is a finite amount of memory, a finite amount of disk capacity, a finite amount of cores, and then you will be eventually oversubscribing that resource and creating a problem, all right? You're supposed to know those things, but you don't, right? You care about physics or chemistry or whatever it is. So then another one related with this is, now you're playing with this infrastructure, but I love the relationship that I have with this cloud provider, for example, so I want to continue doing my business, but the cloud provider is going to change at some point the architecture, their software, and so on, so now you need to keep up with that. So that's an important aspect as well that you should do. And similar to the profiling and monitoring tools, it's the poor understanding of utilization of those components and also performance metrics. So one thing is how busy that is, and one other thing is how efficiently you're using that. They are not the same. So it's important to understand those things. The way I look at this is you're paying some money for getting something done. You want to pay the least amount of money and make the most amount of work, okay? Or within those resources that you have, try to complete your work as fast as possible. So this is very important. And obviously now here we can go and complain against the system administrators by saying, hey, they don't get proper user support, for example, right? So that's the finger pointing, you know. When an error happens, the system administrator says it's fault of the users. Well, the users say, well, but you're not supporting me, right? So then they're just fighting all day long, right? Okay. And then finally, you got involuntary reckless user behavior. By involuntarily, it means that they didn't create the problem on purpose. You know, it just happened, and then sometimes, you know, it could be perceived as being abusive, a user that is abusive of the systems. So, and it's somewhat like a summary, a way of perceiving how the user is doing things, right? So I think this one is a really very important one, slide. Okay, now we're switching gears to type of problems. So there is misconfiguration problems. You can detect those in early stages, and I usually call this thing like the infrastructure by hardware and software readiness, and to get it ready for the production, okay? So those are issues that happen usually at the beginning, and then you fix them, and those issues will, from a frequency standpoint, they just happen really at the beginning and one time, and that's it, you know? But I don't know how familiar you guys are in terms of having a machine, a cluster, that it's kind of like a Frankenstein build because it did not have homogeneous type of hardware all over the place. So you order, say, 200 motherboards, and you get 100 of a certain hardware revision, and then another of another hardware revision, and then this one then goes tied up with a particular BIOS version, and this other one goes with another BIOS version. That's the reality, you know? Because they deliver to you the first batch, and then in 3 months from now, they deliver the other batch. You expect that thing, the second batch, to be the same as the first one, and it isn't. And the memory DIMMs are different type, you know, and so on. So if you really pay close attention to these things, you don't get a perfectly homogeneous hardware, and tied up with that, you don't get the perfectly homogeneous software. So you have to live with that, all right? So I don't know if you realize about that, but that happens. Also, on the CPU side, when you're getting the CPUs, they are not all perfectly equal. You run a benchmark across a bunch of CPUs, and you will get a performance variability. And you know, there are yield differences and things like that, so you don't get anything perfectly the same, okay? So you have to deal with those things. You could even have, between one system and another, you could have even a delta of performance up to, say, 5 to 7%, and you have to live with that, all right? Another important thing is underpopulated systems. So you got a bunch of slots where you can put devices, and you just put it one or two. You don't fully populate. When you don't fully populate, usually there is a preference of putting the device in a particular slot. If you don't put it in that slot, things will be suboptimal. So usually there is sometimes on memory DIMMs, they put one DIMM slot in blue and then the others in black. So it's a way of telling you if it's underpopulated, just put it on the blue. But if it's fully populated, you put it on all. Many times people will think, I don't care where it needs to go, I'll put it whatever place, and then that thing will underperform. It will work, but it will underperform. So that's an issue that happens with underpopulated systems. Or like imagine that you got multiple slots to put network cards, and you're not gonna put all the network cards, you're just gonna put one. So then now your application, some of the processes that happen on this side, they have a harder time to get there. So then it's gonna affect your performance because it's underpopulated. Same thing happens with the software stacks. This is a problem that has to do really with the way that we build software. You know, there's one layer and then another, and then these layers by different organizations that have different release cycles. And ideally, then you need to have them all working together, and then everybody goes on their own. And then it's on your end to integrate the whole thing, test it out, and make sure that that is good, and so on. And you don't touch that afterwards, right? So this is another very important problem that always happens. This kind of release incompatibilities. It's unavoidable. You can even see this, for example, between the coupling of firmware, software, and the driver. If you ask the people that is releasing the driver and you ask which firmware version they use, it's not going to match the firmware version that you're going to have. You may even have a newer firmware version than the one that was used for the development of the driver version. So right there, I'm telling you, you have an incompatibility that you have to live with. What I'm trying to tell you with all of these things is, it's very normal that things fail, because nothing is perfect, and you need to live with that, all right? And then we'll get into quantifying, how likely it's to run into failure. So when you install something, you may have an incomplete installation, you forgot, or you didn't do the right tuning, and you also did not complete thoroughly your validation. So all of those things happen, and those introduce problems. All right, unplanned downtime, it basically means even if you try to do your best, shit happens, and how you deal with that. We're not talking about it, but we are going to acknowledge that problems happen. And this is the unplanned thing. And therefore, there are events that happen at the hardware side, events that happen on the software side, and what you want then is thinking in terms of how to fix them, and the first thing is you need to detect that. But many times, errors happen in a way that it's kind of silent, like there is no trace of the error. But something stopped working, so now you start debugging that thing, and then you think, oh, this is not working. How come I didn't have a log that it was reporting that issue? So this is kind of like a silent error, okay? So then it makes it harder to realize about that thing, and you've been running your things with that thing, that problem already existing, and only when you have something that tries to use that and it doesn't work, then it fails. Your thing, but that component, it was already dead, okay? And you didn't have a way of detecting it. That happens, both hardware and software, okay? And that can happen also because it doesn't need to completely stop working. You could have that performance degradation, but you want things not only to work, but perform. All right, so now we're getting to the degradation. The degradation is it could be a subjective thing, because it's about saying how good enough it needs to be. So at the end, it requires to have a good understanding from an architecture standpoint about how that thing was designed, what it was meant to do, what is the performance it was meant to do, get that number written down, and then say, my applications need to go and hit, up to, say, I'll feel comfortable if I am able to hit, say, 80% of that theoretical number, or 60% of that theoretical number, but not 10% of that theoretical number. So you're the one that's going to decide, I'm putting a threshold at, say, 60% or 70%, but if I'm not getting, say, 50 or 60%, I consider that that's a problem, okay? So, for example, imagine that a PCI device, when you boot the system, it trains the BIOS on the firmware, it trains the speed at which it needs to run, it trains with a certain amount of width of links. You could run into a situation where that PCI device was not properly plugged in, and therefore, when it does the training and negotiation of the speeds, it will downgrade the speed. Still, that thing is working. It's working at half the bandwidth that it can do. An application may not be bandwidth bound, so that your application is fine and so on, but then you could have another application that is running properly, that is bandwidth bound, and then that one will suffer the bandwidth issue. You had the issue right from the beginning, but you had no complaint. But if you go and look at and inspect the PCIe spec on that thing, it'll tell you, hey, it got downgraded to only from the 16 lanes to 8, or from Gen 5 to Gen 4, and it's already there, the information, but you didn't even realize, your application didn't complain, they just were going, but slowly, right? But you have to think, is this 8 gigabytes per second that I'm getting the right thing? Well, that thing is supposed to go up to 25 gigabytes per second, so you're at 1/3 of what it's capable. So you paid for something, but you're not even using it. All right, so this is kind of a summary of utilization metrics, and then you will define a maximum utilization, which is an architecture parameter, and then these are examples. Amount of processing or amount of capacity, and then these are more on the performance side, so you need to understand from a performance standpoint, what it's capable of, and look at how fast it can run or how much energy it can consume. These are just examples, okay? These are just ideas on figuring out, from a degradation standpoint, am I using the capacity that it has, this thing, to its full extent, or is it running as fast as it should run? So get used to define both utilization metrics and performance metrics. All right. And now we get into last part of classification, which is how often a problem happens, all right? So we got rare events. So those events, subjectively, I could say this is an error that I see happening only once a year. Okay? You could say a rare event needs to happen only once in the entire life cycle of the data center, which is, say, 3-4 years. It's a subjective thing, but I'm saying it's, say, once a year. So I'm not going to put some solution for something that happens once a year. I'll just kind of do that reset, and that's it. I just need to do that once a year, and that's it, right? So these are very unlikely events. Another way of calling it's like a corner case, so a situation that is very convoluted, or we occasionally run it or rarely run into that. Some of those are preventable. So if you know that something is kind of not working well, then don't try to use things that way. And it's a very awkward way of using the system. So let's put process in place so you never run things in a way that you stress things that way that is going to create that problem. And we should be able to live with that. Then there are problems that also happen in terms of amount of times, small amount of times, and they happen at the very early stages when you're trying to set up the machines, configure them, and so on, right? And then, as rare events, you've got also unplanned disasters. As an example, a poor disaster recovery plan, have it in place. If you don't have if you have poor automation, relying on manual processes, until you realize, oh yeah, I'm running into this, I do this multiple times, okay, let's automate it, let's make a scripts. And once you've done that, then you never run into those issues again. And then when you're designing your architecture, your platform, not having sufficient paths, and then you have like single points of failure, so then it makes your solution weak. And then you have to harden that, have other alternative, supplementary or complementary techniques to try to avoid those issues. So those issues will happen rarely. So that's what I meant by they are preventable. So there are solutions for those things. Okay, we're increasing the frequency. We go into occasional. I classify them as events that happen on a monthly basis or on a quarterly basis. Sometimes it's you got a business with somebody that they are rolling a new release on a quarterly basis of software. You install that thing and things break. Now you need to go fix it. Well, you got some fixes in place, but now you're breaking some other things. So those things happen on a monthly or on a quarterly basis when you're rolling the new software, okay? You're not usually rolling new hardware on a quarterly basis, but it's possible that you do upgrades, of your infrastructure, whatever patches you're applying on a certain cadence. And I don't know, you guys, for example, roll images, having enabled to go into the repository, and when it sees that there is a difference of packages between what's in the repo there, then just download and install, and in an automatic fashion, always get in the current stage, and the current stage is always constantly broken, right? So usually don't let that happen, right? Again, occasional problems are also this shared resource storage on network that impacts other users. And this can be also an issue, like you don't control the power, somebody else is controlling the power, and then they have to do maintenance or things like that, or they don't have properly supplying the energy or the cooling, and then that hurts on your infrastructure. So those things happen. It can happen, especially on the power side, can happen more frequently. And then final ones is things that happen all the time, okay, constantly. So this can happen even on an hourly basis. Now, you may think, how it can happen on an hourly basis? This is where it gets into the larger scale, okay? Once we go into a very larger scale, these things are magnified, okay? They really happen very often. So these are issues that you may see on a daily basis at small scale, but at larger scale, it will be accelerated, and then it happens more on an hourly basis. And this is important, because when you're running workloads, they're going to get disrupted on an hourly basis, and this is hard, all right? So these event errors do not happen necessarily on the same machine. So that's basically, you're running a job across a lot of machines, so the error can happen at any machine. And because your application requires everybody working properly, you only need one guy, one hardware component, one software layer, something to go wrong, the whole job goes down. As simple as that, okay? So it's highly disrupted, and it's, it can happen two things. Again, either something stops working or something stops performing. Like it works, but it underperforms. And you just need one component to underperform for the entire job running everywhere to get slowed down, right? So here are some approaches for trying to overcome some of those errors, like, okay, so if you know that something is going to fail and it's going to fail in a blocking way, I better have some checkpointing, so whatever work I get done, I save that, and then when I can restart the job, then I start from that point, right? Other type of solutions is fault tolerance, right? So there are cheaper and more expensive ways, but think on hardware-based, now it's becoming very expensive because each of these machines are really expensive. So having a machine down, it's a lot of money living on the table that is not making money. So this is an important thing to consider nowadays on these very expensive systems. All right, and then we're switching to another topic, which is computing or assessing what is the likelihood of having problems, all right? You don't need to freak out, but it's easy math, and it's very easy to see the numbers and understand them, and you'll see that things happen very, very often, all right? So take as an, basically it's the Poisson distribution that is used for assessing, what is the likelihood of a problem happening in a certain amount of time. That's all it is. And now you can think, well, it can happen the problem on this device, or on this other, or on this layer, or on this other layer, and so on. So at the end, it's what is the likelihood of a problem happening on the machine. So it's the combination of all of those hardware components, software layers, user problems, all of that. What is the likelihood of any of that happening, right? So when you're combining all of those things, any of those problems can happen in an independent way, None of those problems will happen at the same time, in a coordinated fashion, like a hardware issue happening at the same time as the user issue. Hardware problems happen independently from the user creating problems, and the software happens independently of the hardware working or not working, and so on, right? So take as an example, for example, here, imagine that I have, 4 times in a year a disk failing, okay? Is that reasonable? Maybe. I mean, you could think, no, a drive may fail every 6 years, but this is just an example. So then you can compute, the rate of failures. So here it comes this number that is hard to understand, but if you do the inverse, you can say, what is the time between one failure and the next? So this number can translate into some of this amount of hours. 7,000 hours, it's approximately 1 year, okay? So it's basically trying to say that between one failure and the next is going to happen one year, okay? Then you can ask, with some of these kind of rates of failure that is easy for you to estimate, then you can start asking questions, okay, what is the probability that the machine will have one hardware disk failure in a certain amount of time, such as, say, 24 hours? So then you can calculate that, and it told us that, okay, the chance that a drive will fail in 24 hours, in the next 24 hours, is only 0.3%. Okay, so I'm safe. I don't need to worry about this. Okay, now, what is the probability that the machine will have 0 hardware disk failures within 24 hours? So it's another inverse way of asking that, and then it says 99.63% of chance. So I'm very sure that I don't need to worry too much about this in this next 24 hours for this machine, because I'm asking for just that drive. All right, now let's complicate things. What is the likelihood of a particular type of problem happening on any machine in the cluster? So then you could say either happening on this one, or happening on this one, or happening on this one. So then the or, you substitute by the plus. And now that problem that we were talking that happened on 0.3% chance in 24 hours, now on 1,000 machines, now we're talking 36% chance. So now you could start thinking, do I have the need to have a system administrator, so to speak, that is all day long dedicated to changing drives, right? Because there's a 36% chance that on a daily basis, I will have to go and replace a drive. And now we're just asking for one drive, all right? Now, another way you could ask the question also is, what is the probability of no machine failing in a certain amount of time, all right? So then it's the probability of 0 failures in that certain amount of time. So when you calculate that for the drive within 1 day for 1,000 machines, so it was 2.58% chance. So in other ways, there is something like 97% chance that you're going to have to go and replace a drive. Okay? Should you start putting processes in place to take care of these things? Maybe at small scale not, but at larger scale, yes. All right? Okay, let's complicate things. Now imagine that I have a cluster with 1,000 servers, and these are the computers, 2 CPUs, 8 DIMMs per CPU, 8 GPUs with its HBM. So it is nothing fancy. Then I got the network attached on the CPU side, 8 NICs per GPU as well, certain amount of NVMEs. I got, for simplification purposes, 5 layers of system software, which is not true. You got 10 times that. And then 5 user layers, which is not true. You may have 20 times that, okay? And then you have, say, a total of, say, 1,000 users, and at a given time, I got 50 users running concurrently jobs, for example, okay? All right, what's the likelihood of something failing, right? So now let's put some numbers in terms of the failure rate. So for example, you know, what is, how many failures I can have in 1 year for a CPU? So I just put, say, 1, only once, okay? Maybe it's less than that. It's okay, just put whatever numbers you want. What's the likelihood, like for example, how many problems I think I can have on the NICs per year? Say 2 problems per year, okay? How many problems I can have on drives per year? Only one. How many problems I think I'm gonna have on the, anything on the software layer? Maybe 2 problems per year. You know, these are very conservative numbers. You can throw in there whatever numbers you want. But let's assume that these were good numbers. Numbers that they are conservative. I think these are something fairly reliable. Let's go with it and calculate, you know, what is the probability of having no problems on any of those machines? So no problems here, and no problems there, and no problems there, and no problem there, on all those 1,000 machines for a certain amount of time, say 24 hours or 1 month. Okay, so let's calculate that probability. And then basically, I put that in a table. Here is CPU tier, GPU tier, network tier, storage on the CPU network, and then, okay, this is the total system hardware. What's the probability of not failing within, say, 1 hour? So, okay, 99% chance of not failing. Now, what is the probability of not failing in 24 hours? 83%. Not failing in 7 days? 29%. And in a month, 0.52. So what is telling you that it's guaranteed, you know, I mean, just look at even 7 days, like 1 week, you know. You got only 30% chance of not failing. Or in other words, you got 70% chance that it's going to have a failure in 7 days, in 7 hours, in 7 days. Okay? That was just purely considering problems on the hardware side. Now we can do the same on the system software, and then on the user software, I can combine them, and then, okay, what is the probability of not having a problem in 1,000 servers? Problems only due to software. So 99% of not having a problem, 95%, 71, 24%. So 75% of chances that a user, that a user software or a system software is going to have a problem. It's going to create a problem, all right? And then now we go into the user errors. So what is the likelihood of, on any of those machines, of not having a problem in, say, 7 days? So it's 50%. So it's a way of saying that in 7 days, I have a 50% chance of a user creating a problem. All right? Now, let's put that all together, hardware errors and user errors and all that. And then I did that for, say, having a cluster of 1 machine, which doesn't make sense, but it's a cluster of 1 machine, a cluster of 10 machines, 100 machines, and 1,000 machines. Okay, so for example, for 100 machines, what is the probability of not having any problem across any of those system hardware or system software or the user errors, combining all of that in 24 hours? 0. It's telling you it is guaranteed to fail in 24 hours, getting one kind of problem, whatever it is, you know. Now let's go to 1,000 machines. You know, what is the probability of not having a problem of any kind in 1 hour? 0. What does it mean is that if I'm trying to run a job at larger scale with 1,000 machines, there is no way you're going to get that run to survive 1 hour. No way. Just following this. Now, how wrong am I in this? This is a picture of a chart from Meta that they published around the end of last year on 2 of their clusters where they're running larger scale with a certain amount of GPUs. And in this line in here, it tells you the mean time to failure, when a failure is going to happen. And you can see that the larger the scale, the mean time to failure is going down. So here they are into the, 2 hours. They can make a job survive something like 2 hours. So basically what I'm trying to find out is, can my job survive 1 hour? No, you can't. It's impossible. Maybe you don't have that problem now. But again, if in the future you got a 1,000-node cluster, think that problems are going to happen on an hourly basis, and your jobs are not going to complete like your jobs usually, these training jobs for foundational models, they usually last 1 month, 2 months, or something like that. Can you imagine a job that needs to complete in 30 days, failing every hour? All right, so that finishes the presentation. And if you have questions, I'm more than happy to answer.
That's awesome. Going.
Hi, thank you for the presentation. I really enjoy it.
Thank you.
I'm a system administrator in a small cluster, but
Good.
I can see very well that. But just to say something, because okay, the probability of something failing in 1 hour is 0, but we don't have here the how dramatic is this error, because it could be an error that doesn't affect really, it affects the performance or
yes.
So you are not aware of, so your job will finish in 30 days maybe.
Right.
In that, just this.
So,
this kind of,
but that's not a question; it's just a comment.
yeah, it's a comment. It's a comment. It's a comment that it is hard to how do you measure how the errors affect? Because I think this category of errors, it's really interesting.
Yes.
What is interesting too is good, just to calculate the likelihood of the errors, separating the errors that will be more dramatic, that the other ones that, okay, maybe, all right, the performance is not good, but it's not so low that as to be, we can ignore that kind of errors, because the zero error will it's impossible. That's my point.
I like to say that when you're used to work at larger scale, any little issue, you can see it fairly easily. Like that thing is not running as it should, and so now if you look into it and start doing root cause analysis, debugging that issue, you think, oh, I found the issue, and then when you look into running into that issue at small scale, it's not necessarily a high impact thing, but at larger scale, it gets magnified. So actually, I have a lot of times a difficulty in having a conversation with somebody that is not used to work at very large scale, because you're talking Chinese, so to speak. The type of problem you're talking and the kind of the severity of the problem, they are not experienced at that scale. They don't see, how that particular type of degradation has such a large impact on something, right? So that's why it can be, I mentioned it, it's a subjective thing. So when I was talking about this one in here, okay, here, you have to define a percentage based on your own opinion at a certain scale of what is acceptable and what it is not. For example, I do know certain organizations that you could get fired if you run a job with a parallel efficiency less than 80%. Okay? So whoever said that, I kind of agree with that. All right? You don't want to run a job at 50% of parallel efficiency. That basically means that you're doing something wrong. Obviously, if you have a way of proving that something is misconfigured, then you're saving your butt. But if you didn't do the right thing, then you better run your job at the right scale, because you're leaving on the table a lot of those resources that other people could use for productive jobs. So again, that's a subjective thing. But usually when I try to run something, I will not run it below 80% of parallel efficiency, for example. And what that basically means is, if I got a collective operation that is going to have a long tail after a certain scale, and then that's going to make my parallel efficiency to go from 80 to 75, that is telling me that given that kind of tail on that collective operation, unless I get that optimized by having a different algorithm or doing something here or there, like interrupt handling in another way, whatever it is, to reduce that tail, then I will be constrained to run my jobs at a certain scale and not go beyond that. Sometimes you could forget on one machine to put performance mode because you do it manually. Such a stupid thing to do, right? So now you got all machines in performance mode and one in power saving. So now you have the MPI call happening, and then it used to trigger interrupt, and then it goes, yeah, I'll do it, but at my rate, because I'm in power save mode, right? So now that's the one that's creating the tail. That's just an example of things that happen, Nobody's on purpose trying to hijack the system, but we just make plenty of errors.
Those numbers are based on a 1,000 node machine. So if you look at the top 500, and you get the top 100 out of the 500, the scale it's slightly different than just 1,000 nodes, right? So
actually, on this aspect, you know that you do the top 500 submissions. They changed the impact benchmark because they couldn't afford to run it for, say, 48 or 72 hours because it was guaranteed to fail in, say, 5 to 6 hours. So now they needed to do the shorter version of the impact to just run a few columns and then get that number and cross the fingers that while you're collecting that, it doesn't fail something. So not anymore. You can run at larger scale an exaflop system for literally 24 hours consecutively. It doesn't hold.
More comments, questions?
Very nice presentation, because we tend to explain on presentations or what the things that we do well, and it's very nice to talk about errors and how to. Yeah. So thank you. I would like if you could comment more on the recoverability. So what's your thoughts and your methodologies once that we know that we have these issues? If you could, yeah.
Okay, so in theory, this is a technical presentation, not a business or a presentation. So, but I had that slide there that says, if you want to know how to solve the problem, talk to me. Okay? The idea was to make you aware of the problems that you may have or not. I will tell you, though, that it's not easy. Okay? There are no patents out there. It's all secret sauce. It's all highly customized for their own systems. Say, Google have their own hardware, their own software stacks, their own process, and so on. So then they have their own kind of problems, right? So they have implemented their own detecting and fixing problems, right? Automated, call it, say, self-healing. What I'm trying to do is the same thing, but not for those custom products, because everybody does their own thing. So I'm more going towards the x86 solution, regular GPUs that you can buy, regular open software stacks, things like that. But it's very difficult, and I'll tell you why it's very difficult. I don't talk about that in here, but user problems, you can see them coming. They can be building up. So you can put preventive measures, call it guardrails if you want, or things like that. For example, a user doesn't understand that they have a limited capacity of a storage. Then they can keep doing checkpoints, and they're saving all the checkpoints. Well, sorry, you got already a valid checkpoint, why you need the other ones, right? Or you got a container you're loading, then another one that you're loading, and then, okay, you don't have unlimited disk space, so get rid of the least recently utilized containers, so then you leave a space in there. If you don't do those cleanup things and so on, you can see things are building up. Memory consumption, you can see it building up in a matter of seconds. So when something happens in the second range or few seconds or something like that, you can see things, you can see the trend, and then you can put measures to try to prevent those issues. Another thing is when you're dealing with things at the system software level or at the hardware level, those things fail fast. So even if you were trying to poll, say, give me the state, give me the state, give me the state, give me the state, between one sample and the other one, it already failed, right? So it's difficult to actually catch the issue when it happens and then trigger a fix immediately, so anything above it doesn't trigger a failure as well. So I'm easy to talk on this because it's a hard problem, but that's actually what I'm trying to do. Solving in real time these issues to provide better continuity. Not to solve all the problems, but to try to fix as many of those, so then we can try to go maybe from 1 hour of execution, solid at 1,000 nodes, to say 2 hours, by just getting some of those problems that happen very frequently handled. You know, that's kind of the challenge.
I would say that from the user problems, the most frequently I think I found in small-scale clusters as ours, 100 nodes or so, I think is the scalability problem. They think if they run their codes in twice the cores, it will run twice fast. And if they run 10 more cores, 10 times, they will run 10 times faster, and so it's not like this. And I think it's the most common problem I found in regarding the user education about using the cluster, which you mentioned.
Yeah, I don't talk about that part in here, but it's an important aspect as well, yes. I'll give you an example that is similar to this, but on the development side, okay? Both hardware side and software side. When an architect, and I'm talking from my own experience, working at all of these semiconductor companies, when you design a chip, you're usually not designing the chip thinking of using the chip at larger scale. You need to simplify your life, and then you're going to build environments and tests and things like that, running at smaller scale, and then you will validate those things. Then you get the business guys that say, now I'm going to use this at scale. So because this thing was not designed nor tested at scale, you are actually finding out the issues of not having this properly designed at larger scale. Same thing happens with the algorithms. You will implement an algorithm and test it out in your own cluster, which is at small scale. Now somebody will grab that thing and run it at larger scale. So now you're going to run into a lot of problems associated with at the scale that you're running. When you get to learn those things, usually what you will do is you'll have like something that says, if I'm running at this scale, the most suitable algorithm is this. When I'm running at this scale, the most suitable algorithm is this, and so on. So that shows you then the maturity of the software stack when it is capable of understanding and discovering what is the scale you're trying to run things, and then give you the most optimal implementation, which is not necessarily the right one across all the scales. So at every scale, you need to do things in a slightly differently. But we all tend to kind of grab something that works at one scale and then use it at larger scale. And then that's when problems happen as well.
Have time for just one more question. I know that it's an amazing debate.
Thank you. Good. Great presentation first. No one likes to discuss about failure.
Yes.
So that's excellent that you are covering this topic today. First point.
Great.
Can you go back to the slide with the curve and so on?
Which one?
With all your summary.
The last one?
Yes, last one.
Good.
Please. Yes.
This one?
No,
I'm kidding.
The previous one. Yes, this one. Here you are considering hardware, software failure, user misbehavior. Have you noticed improvement by bringing DLC, so water cooling?
Bringing?
Stability of platform, so I mean mainly the system hardware errors, fewer errors with DLC. Because I'm...
with what?
With DLC, direct liquid cooling. Survey we have done at HPE is that it's a huge impact on stability. On GPU, it's something that goes fast but can be fragile. And when we move to an environment where the cooling of component is better, it seems that we could sustain longer workload even on large systems. So maybe this is a topic that could be included in your next year presentation.
No, so I've been in there. When I was at AMD, for example, literally I was putting CPUs into an oven, okay, and putting the temperature at, say, 40 Celsius degrees, like thinking on the environment, use case of putting racks into a container and putting it in the middle of the desert, okay? And usually you look at the specs, and it will tell you this particular chip, you should not operate it at a room temperature that is above a certain number and below a certain number, right? So that's basically telling you that there is an impact from a thermal standpoint. When you are operating at higher temperatures, there is a higher leakage current, okay? And then thermal protections can kick in, and then it will do what's called thermal throttling. By having a good cooling solution, by that I mean that I don't care whether you do air cool or liquid cool or immersion cooling, but as long as you're able to control properly your temperature, that you're good. So if your cooling solution is cheaper and doing what it needs to do in terms of making sure that you are under the right temperatures, you're good. So if an air-cooled solution is properly implemented, as long as you're capable of staying in the range of the temperatures that is recommended, then you're going to be good. If they do a bad job, because you depend on the fans working properly and the BIOS didn't do a good job at regulating the fan speed, on top of making it noisy, but in the data center, just the system administrators have to walk in, you don't have to. But the thing is, as long as that thing is properly operating in temperatures, then you're good, right? So cooling is important because it can affect the performance and the stability of the chips. Yes, I totally agree. But I wouldn't say that thanks to liquid cooling, it's better than others. You could think, as I said, immersion cooling too. Two-phase immersion cooling as well and things like that. The most important thing is to make sure that you stay under the right temperatures. That's the most important thing. There is also problems with liquid cooling, right? There is leakage problems, the spill and things like that. So every solution has its own challenges. But as long as you stay, the important message here is have the chip stay in the right range of temperatures. Agreed. Otherwise, it increases the rate of failures of that chip. Yes, absolutely. Because think that from a manufacturing point of view, you're also going to be testing that under a very constant environment, super constant. You get the chip, you got a hose, usually, or Peltier effect, and you control perfectly the temperature. And then you will test the chip, all the functions, to make sure that that thing works properly, And then that's how you do binning also, So if your environment is not stable from a thermal standpoint, then that thing is operating in a range that was not supposed to be. And that's when you get problems. Yep.
Thank you so much, Joshua.
Okay.